Hello and welcome to the next lecture about the Laplace transform. Today we're looking at some useful formulas that will help us to compute Laplace transform a lot faster than just computing the integral. If you remember, when you were just started studying the derivatives, you learned about this limit definition of a derivative. And then you only use it once to build up the table of derivatives, and then since then you always use that table to compute all of the derivatives and all of the antiderivatives. So today we're doing something very similar. We're building up a table of Laplace transforms for very basic functions, and then we're going to use that table to compute the Laplace transform and to compute inverse Laplace transform later on. So the first function we're going to consider today is a function that is a constant. So the simplest constant there is constant 1. And I'm going to define a function to be constant to be for all t greater or equal than 0. And you might say, well, what happens before 0? Well, before 0, all of the functions are supposed to be 0. And that's what this function is doing. Now, why is it so that the functions are supposed to be 0? Well, Laplace transform is used in the theory of signal analysis. And mainly all of the signals that come to us at certain predetermined moment. And in the past, there was no signal. And this line of thinking is deeply embedded into Laplace transform in this assumption that all of the functions before 0, they're always 0. This function has a name. It's called a Heaviside function. Or a unit step function. In the package Mathematica that we're going to use extensively, it's called the Heaviside theta function. With the introduction of this function, we can say that all of those functions in the framework of Laplace transforms are considered to be pre-multiplied by this function h of t. So, if we're talking about f of t, then f of t is actually h of t times f of t. And this is done to emphasize that all of the functions before t equals 0 should be 0. And if the original function f of t, say an exponential function or cosine function, actually is non-zero for negative t, then this product will force it to be 0. And this assumption is very important when we start considering shift theorems, and you will see that this function h of t pops out of nowhere. Well, it's not out of nowhere, it's because we actually consider every function to be this kind of product. So what's the Laplace transform of h of t? Well, since we haven't built up the table, here we have to do the integral. Well, that's going to be the integral from 0 to infinity h of t times e to the minus st dt. Well, since h of t is always 1 for t greater or equal than 0, this is basically the integral from 0 to infinity of e to the minus st. Well, these integrals have to be computed as limits. And the antiderivative for this function is minus 1 over s e to the minus st evaluated from 0 to capital T. Well, oops, I apologize. I have to put the limit in front of it. Well, when we plug in capital T in 0, we get this. It's the limit. As capital T goes to infinity, we get minus 1 over s e to the minus s capital T plus, because it's negative, we subtract a negative quantity, plus 1 over s, which is what this formula yields if we plug in t equals 0. You can imagine that this limit would not exist for s negative, because then this product, for s equals 0, this limit doesn't exist because 1 over s is not defined. For s being negative, this product is actually positive, and as t grows, this will actually grow to infinity, so the limit doesn't exist either. For s being positive, this limit is defined because when t goes to infinity, this is going to be e to the very, very negative power, which is very, very close to 0. So I should say that only for s greater than 0, this limit is 1 over s, and I should add only for s greater than 0. I did say a while ago that this integral may not be defined for some values of s, and that's exactly what happens here. For values of s 0 or negative, this integral is undefined, or it doesn't converge, and so the Laplace transform only exists for positive s. Next function that we're going to consider is the shifted Heaviside function, h of t minus alpha, where alpha is considered to be a positive constant. We only shift to the right, we never shift to the left, because then if we shift to the left, we technically start getting values that are non-zero for negative t. Well, that's really not that hard either. We have a function that sort of shifts to 1, not at t equals 0, but at t equals alpha. So the function is 0 all the way up to alpha, and at alpha it switches to be 1. We can define h of t minus alpha as a function that's 1 if t is greater or equal than alpha, and 0 if t is less than alpha. The Laplace transform of this function is still an integral from 0 to infinity, because that's how the Laplace transform is defined, and we're integrating h of t minus alpha times e to the minus st dt. Well, since this function is 0 up to alpha, this is the same as the integral from alpha to infinity of 1 times e to the minus st dt. Well, this has the same antiderivative, which is minus 1 over s e to the minus st evaluated from alpha to infinity. Notice I didn't write the limit again. Well, I'm doing that to shorten the notation. So this is just a notation that I'm actually behind the scenes evaluating the limit. When I plug in alpha, then I just get e to the minus alpha s divided by s. When I plug in infinity, I get 0 for positive s. Again, this only exists if s is assumed to be greater than 0. And that's the value of the Laplace transform. Notice it's very similar to the Laplace transform I got before. Before, I've got 1 over s right here. And now, shifting it by alpha, I get this extra factor, e to the minus alpha s. This will actually be one of the theorems that we're going to discuss later, which will prove that this is actually a general pattern when you're shifting your functions. So what are the functions we can compute Laplace transform of? Well, we have elementary functions like polynomials, trig functions, exponential functions, and that's what we're going to do. So first let's consider e to the alpha t. Well, by definition, again, it's an integral from 0 to infinity, e to the alpha t times e to the minus st dt. We can kind of say that that's the same as the integral of e to the minus s minus alpha times t dt. Well, the antiderivative of this is minus 1 over s minus alpha e to the minus s minus alpha t evaluated from 0 to infinity. Again, I'm going to skip doing the limits. So I'm just going to say that at infinity, exponential function will converge to 0, and at 0, I have e to the 0 is just 1, so the overall Laplace transform is 1 over s minus alpha. And again, this will only work if s minus alpha is positive, which means that s is greater than alpha. So this Laplace transform only exists for s greater than alpha. Notice an interesting thing right here. We have a shift producing an extra factor of e to the minus alpha s, and say taking the function h of t and multiplying by e to the alpha t produced a shift. Okay, moving on to the trigonometric functions. You can imagine I will just jump into this integration, and after a little while I'll get a formula. Instead, I'm going to use a clever trick. If you remember, computing the integrals like cosine times exponential function involved double integration by parts and then solving an algebraic equation, and this is why we get the integral. Well, that's way too long. There is an easier way to do it. And since that's the overall thing of the Laplace transform, we're just doing things an easier way, although a little bit less direct. Let's use the earliest formula. If you remember, the earliest formula said this: e to the I omega t would be a cosine of omega t plus I sine of omega t. And instead of computing the Laplace transform for cosine and sine separately, I'm just going to compute the Laplace transform of e to the I omega t. You might say, well, how do I separate the Laplace transform of cosine from the Laplace transform of sine? Well, I'm just going to take the real part, and that will be the Laplace transform of cosine, and the imaginary part will be the Laplace transform of sine. So this is an integral from 0 to infinity of e to the I omega t times e to the minus st dt. This equals an integral of a singular exponential function e to the minus, inside the parentheses I have s minus I omega, and the whole thing multiplied by t, integrate with dt. As before, the antiderivative is just going to be minus 1 over s minus I omega multiplied by e to the minus s minus I omega t evaluated from 0 to infinity. And here's an interesting fact. I can write this as minus 1 over s minus I omega, and I'm going to separate it into e to the minus st times e to the I omega t, evaluated for t from 0 to infinity. When t is equal to 0, this whole thing is going to be just 1 over s minus I omega. Well, what happens when t goes to infinity? Well, the second exponential function is going to be the complex number with absolute value 1. But the first exponential function, e to the minus st, will converge to 0, again, if s is greater than 0. So this ends up being just 1 over s minus I omega. You might imagine this is a difficult number to separate the real and imaginary part. So what we have to do is we have to multiply by conjugate s plus I omega divided by s minus I omega multiplied by s plus I omega. And by the magic of the complex arithmetic, this turns into s plus I omega divided by s squared plus omega squared. Well, this is very easy now to separate the real part and imaginary part. And then we can say that the Laplace transform of the cosine of omega t is going to be equal to s over s squared plus omega squared. And the Laplace transform of the sine of omega t is going to be omega over s squared plus omega squared. And this is only true if s is greater than 0. Despite the fact that this Laplace transform is defined for all values of s as long as omega is non-zero, we still have to consider the fact that because we're looking at the improper integrals, and the improper integral will not converge if s is negative in this case. Alright, let's switch to polynomials. Well, the easiest polynomial there is just a linear function, f of t equals t. So the Laplace transform of it is quite straightforward. All I have to do is to compute this integral. Well, this integral needs integration by parts. I'll have to set u to be t and dv to be e to the minus st dt. That makes du just dt, and v is minus 1 over s e to the minus st. So this integral transforms into a minus t over s e to the minus st evaluated from 0 to infinity. Minus minus turns into plus, the integral from 0 to infinity of 1 over s e to the minus st dt. Well, for t equals 0, this whole thing is going to be 0. So this equation is going to be 0 when t is 0. When s is positive and t goes to infinity, this exponential function will converge to 0. But t will go to infinity. So which one is going to win? Well, we evaluate those integrals with the help of L'Hopital's rule. And the L'Hopital's rule will say that when t goes to 0, exponential function wins and everything converges to 0. So at both endpoints, this expression brings us 0 value. So this equals to 0 minus 1 over s squared e to the minus st evaluated from 0 to infinity. For positive s, when t goes to infinity, exponential function will converge to 0. So the only thing that matters here is the value of this function at 0. So this becomes 1 over s squared for s greater than 0. Alright, this does look a little bit like Heaviside function. When Heaviside function was just 1 over s, the function t is 1 over s squared. So that's interesting if the pattern would repeat itself when we start looking at higher power of t. Okay, let's just go ahead and do it. Again, we apply the definition of the Laplace transform to the function t to the n. This needs integration by parts applied exactly n times. Well, doing that would be actually quite long. We can get away with just doing one integration by parts. So u is just going to be t to the n. dv is e to the minus st dt. This makes du to be n t to the power n minus 1 dt. And v is minus 1 over s e to the minus st. That turns our integral into t to the power n times minus 1 over s e to the minus st evaluated from 0 to infinity. Double minus makes it plus. An integral from 0 to infinity of n over s t to the power n minus 1 e to the minus st dt. Just as before, this quantity will actually converge to 0 at both endpoints. When t equals 0, it's 0 because we have t to the n power. When t goes to infinity, exponential function wins the competition with t to the n and brings everything to 0. So this actually equals 0 plus n over s, and you can see that the integral we have here is actually Laplace transform of t to the power n minus 1. So we got ourselves a recurrence formula. So for example, we can say that the Laplace transform of t squared is going to be 2 over s times the Laplace transform of t, which we do know to be just 1 over s squared, so this becomes 2 over s cubed. What about the Laplace transform of t cubed? Well, that's going to be 3 over s times the Laplace transform of t squared. Well, that becomes 6 over s to the 4th. What about the Laplace transform of t to the 4th? Well, that's going to be 4 over s times the Laplace transform of t cubed, and that becomes 24 over s to the 5th. we can see that this generates a quite recognizable pattern. The Laplace transform of a function t to the power n is going to be simply n factorial over s to the power n plus 1. And again, this only is defined when s is greater than 0. So we've built ourselves quite a few formulas. We have Laplace transform of a simple function that is just a unit step function. We have Laplace transform of a shift and heaviside function. We have exponential function, we have trigonometric functions, and we also have polynomials. Well, what if you have a polynomial that's not just t cubed? What if it's t squared plus 2t, or any sum of the polynomial terms, and maybe let's mix in some exponentials? Well, what happens is that we can use the linearity of the Laplace transform to break down the computation of Laplace transform into smaller bits, just like we do it for derivative. If we need to compute the derivative of a sum, we compute the derivative of each term and then add the derivatives. It's quite true for the Laplace transform as well. So if the Laplace transform of some two functions are pre-computed, well, then any linear combination of these two functions is going to be the integral from 0 to infinity of the linear combination and then we can use the linearity of the integration to say that this is going to be c1 times the integral from 0 to infinity of f1 e to the minus st dt plus c2, the integral from 0 to infinity of f2 e to the minus st. Each one of those integral is a Laplace transform of the respective functions, so it's just going to be the linear combination of the Laplace transforms that we have computed earlier. And that means that we can compute Laplace transforms of polynomials or sums of functions, etc., etc. So these formulas that we just derived above will be actually quite powerful in allowing us to compute Laplace transforms of many functions. I have to mention also a couple of things that are true about a Laplace transform. You notice that for some values of s, the Laplace transform is not defined. There are functions for which Laplace transforms actually do not exist. So let's consider this function. This is the function that rises quite rapidly. And so the Laplace transform will be the integral from 0 to infinity of e to the t squared times e to the minus st dt. And no matter how positive, how great s is, e to the minus st decays to 0 a lot slower than e to the t squared grows. So overall, the integrand is going to be very large and very positive, and this integral is always going to converge to infinity. So this integral never converges. For all values of s. And this function, as a result, doesn't have a Laplace transform. Another thing that we need to note is in most applications, we compute the Laplace transform without knowing what the actual function is. So in these particular problems, we assume that the Laplace transform is actually defined. And we operate on this assumption. And then later on, when we get the actual formula for Laplace transform and we get the inverse Laplace transform, that's when we actually see that a function actually may have a problem. So I would say that in our applications, we assume that the unknown function we try to determine possesses the Laplace transform. For at least some values of s. And only after we obtain the solution, we analyze and see if the Laplace transform actually makes sense. And if it doesn't, well, then the solution method that we chose may actually not result in an appropriate solution and we have to do something different. But most of the time, everything works out quite nicely. Alright, that's enough theory. Let's do some computations. So suppose we need the Laplace transform of this very simple function. It's a sum of three functions. So Laplace transform of f1 of t is just going to be the sum of the Laplace transform, three Laplace transforms of e to the minus 4t plus Laplace transform of t squared plus Laplace transform of the function 1. And you might say, wait a second, we didn't do the function 1. Well, we did. The function 1 right here is the Heaviside function because remember we assumed that everything is 0 for negative t. So f1 is 0 at negative t and everything is multiplied by the Heaviside function. So Laplace transform of 1 is actually Laplace transform of the Heaviside function. Well, this becomes 3 over s plus 4 because that's what the Laplace transform of the e to the minus 4t is, plus 2 over s cubed plus 1 over s. Another quick example. What about these trigonometric functions? Well, they don't look like simple sines and cosines. And before we can actually do something about that, we have to change these functions into just simple sines and cosines. Well, we know the formula for cosine squared. It is 1/2 of 1 plus cosine of 2t. Well, what about the sine 2t times cosine t? Well, that can be converted into 1/2 of sine of 3t plus 1/2 sine of t. This is a trig formula that says this, that the product of sine and cosine, so you have a sine of alpha times cosine of beta, well, that's simply 1/2 of sine of alpha plus beta. I'm going to move it a little bit. Plus sine of alpha minus beta. So applying this formula gets me this sine of 3t and sine of t. Alright, now we can do the Laplace transform. Well, that's just going to be 3/2 of the Laplace transform of the Heaviside function plus 3/2 of the Laplace transform of cosine of 2t plus 1/2 of the Laplace transform of sine of 3t plus 1/2 Laplace transform of sine of t. Well, I get 3/2s for the first function. I get 3/2 times s over s squared plus 4. I get 1/2 times omega, which is 3 over s squared plus omega squared, which is going to be 9, plus 1/2 of 1 over s squared plus 1. Alright, the last function we're going to consider is this hyperbolic sine. So it's not a sine, it's a hyperbolic sine with the h at the end. And it simply means it's this exponential, it's this linear combination of exponential functions. Well, that's just going to be 1/2 Laplace transform of e to the 2t minus 1/2 Laplace transform of e to the minus 2t. So that's going to be 1/2, and it's going to be s minus 2 minus 1/2 s plus 2. And you can imagine that this Laplace transform will only exist for s greater than 2. It's quite easy to compute Laplace transforms of simple functions. What if we are given the Laplace transform and we need to compute the function that this Laplace transform belongs to? Well, we can use the table that we just built up to reverse the Laplace transform and get the function that this Laplace transform is probably originated. In doing so, we really have to assume that the Laplace transforms uniquely identify the functions they come from, and no two functions that are different from each other will have the same Laplace transform. And that requires a theorem, which we're not going to prove, but we're going to assume that it is true. So we have seen that the terms like the first one come from shifted Heaviside functions. The term like 1 over s to the fourth is probably coming from a Laplace transform of t cubed. And the terms like s squared plus 4, well, that looks like a Laplace transform of something like a sine. So the inverse Laplace transform, which we're going to denote L to negative 1 of capital F of s, is going to be the inverse Laplace transform of e to the minus 2s over s plus the inverse Laplace transform of 1 over s to the fourth plus the inverse Laplace transform of 1 over s squared plus 4. Well, these formulas don't quite match exactly the formulas we developed. So I'm going to put in some coefficients. The first one is actually quite easy. It's just a Heaviside function of t minus 2. The second one, well, s to the fourth, if we scroll back, s to the fourth term is the one that should have 6 at the top. And so I'm going to need that. As well, for the s squared plus 4, we're missing the 2 at the top for the function, for the sine function. So what I need to do is to bring these constants inside. But when I multiply by 6, I also have to balance it out by dividing by 6. So this becomes the Heaviside function of t minus 2 plus 1 over 6 t cubed plus 1/2 of sine of 2t. The rest of this lecture I want to devote to looking at the software package that is Mathematica. We're going to use Mathematica extensively, and so I want to show you the capabilities of Mathematica at the example, looking at the examples we just looked at today. So here I have a Mathematica window open, and I'm going to show you how to do things with Mathematica. If you've never seen Mathematica before, it's very unusual in the sense that it's not like the software packages you may have seen before. I apologize in advance for any loud tapping on the keyboard that I'm going to do. So what Mathematica gives you, it gives you the interface with cells. Every cell is a computation block in Mathematica. And you just have to type in your commands. So for example, I can type in the command of plotting a function x squared, where x goes from -1 to 3. And if I press Shift Enter, that evaluates this command and produces a graph. You might be wondering, how did I make the x squared to look like x squared? Well, that's a little bit of a magic of Mathematica. If you don't want to learn the shortcuts that give you the more mathematical look to your formulas, you can just simply use Shift 6, and that will produce the same result as the function x squared. You notice an interesting format to this command. The name of the command plot starts with a capital letter, and every Mathematica command that's built into it starts with a capital letter. Then the parameters for the command, for the function, are inside brackets. This is done to separate the brackets from parentheses. In Mathematica, parentheses is simply just a grouping operator that groups arithmetic operations. So parentheses are only used as an arithmetic operation of grouping a calculation. And for the functions, you have to use brackets. The arguments are separated by commas. So the next thing that comes after the comma is this weird expression curly braces. Well, that's how Mathematica expects you to specify the domain of the plot and also the variable. I can actually change the variable to be anything I want. So I can just say plot g squared, where g goes from -1 to 3. And that doesn't change the plot at all. So we just told Mathematica that g is the variable, g goes from -1 to 3, and we need to be a plot of g squared. So Mathematica is quite comprehensive, and it's very mathematician oriented. And for that reason, it's mostly used by mathematicians. You don't see it in engineering circles a lot. You mostly see MATLAB in engineering circles or straight C++, because these are languages that are very computation oriented. Mathematica is very mathematics oriented. It makes stuff easier for mathematicians. Alright, so what we did today is we used a lot of integration. And so let's plot the Heaviside function, which is called Heaviside theta. So you notice Mathematica gives you a little hint. And so let's just say Heaviside theta, and let's plot it for t going from -2 to 4. And that's a step function. It's 0 before 0 and 1 at 0 and after. So what would be the Laplace transform of this function? Well, Mathematica has a built-in Laplace transform suite, and it has a command that's just Laplace transform. As you can see, it's right here. But instead, I'm just gonna introduce an integrate command that you can use for other computations. So let's compute the Laplace transform of t. So it's t, and Mathematica does not require you to use star or shift 8 to signify a multiplication. It only requires a space between two things if these two things are letters. So if I do ty, well, that's a simple variable that has a name ty. But if I do t space y, then it's t times y. 2t is just 2t, 2 times t. So that's what I mean by Mathematica being very mathematician oriented. So what I need to do is I need to say it's t times the exponential function, which is x in Mathematica, of minus s space t, and we need to evaluate it for t going from 0 to infinity. Mathematica has a built-in keyword for it. Well, that's very weird. Well, Mathematica is being very mathematician oriented. It assumes that the variable you specify are actually quite possibly complex. So here this integral does converge only if s is greater than 0. We can say it that we consider s being greater than 0. And then computes the integral 1 over s squared. Well, that's quite a complicated and clumsy way to do the Laplace transforms from Mathematica. So let's just use the built-in command of, so let's start with Heaviside function. Alright, at this point you might say, well, the Laplace transform needs several parameters. what are those parameters? You can actually ask Mathematica to help you out. So it needs you to supply the expression that you're computing the Laplace transform of. It needs to give you the variable of the function and then the variable of the Laplace transform to output. So I can just say that the function is given in terms of t and I want the Laplace transform in terms of s. That gives me 1 over s. If I change the name of the variable to x, and that's what's going to be the result. Quite simple. So what is a Laplace transform? Of the Heaviside function of t minus alpha. Well, I just entered alpha by pressing escape button A and then escape button again. This is Mathematica's way of entering Greek letters, so escape G, escape will give me gamma. Cool, isn't it? Anyway, so I need Laplace transform in terms of t, and Laplace transform should be output in terms of s. Wait, what's that? Well, here I didn't say to Laplace transform that alpha has to be positive. And the Mathematica assumed the worst, that alpha may be negative. And if I just say that alpha is positive, then the unit step function at minus alpha is going to be 0. So that term is actually 0. And that term is actually 1. So I would need to actually say something to the Laplace transform that I would say that the parameter alpha here is positive. And the Laplace transform also has the assumptions option. Now we can tell it that, well, a is greater than 0. Well, let's try that. That alpha is greater than 0. In this case, it computes the Laplace transform that we just computed. Alright, what else did we do? We did the Laplace transform of functions like a cosine of omega t, and we need in terms of the functions given in terms of t, we need Laplace transform in terms of s, and I'm going to assume that, well, omega is not 0. And here it is. We also wanted the inverse Laplace transform of our example, which was e to the minus 2s over s then there was 1 over s to the 4th that was added, plus 1 over s squared plus 4. Well, this is in terms of s, and we need a function in terms of t. And the result is exactly the same. Well, you might say, well, no, it's not exactly the same. Well, we have a cosine t times sine t. Well, cosine t times sine t is exactly 1/2 of sine of 2t. So in this case, Mathematica just did something different than what we did, but arrived to the same conclusion. Sometimes this might be an inconvenience. The Mathematica will give you an answer that is exactly the same as yours, but it looks very, very different. Just like earlier, before I put the assumptions into my Laplace transform commands, the Mathematica was outputting something that was difficult to interpret and required a little bit of thinking before we can see what is the actual result. So Mathematica, just because it's so universal and so comprehensive and so general, it tries to assume the worst. It works in mysterious ways and gives you an answer that would fit to the best of its abilities the situation that you're given to it. So sometimes you have to be quite careful with what you ask for from Mathematica, and sometimes Mathematica gives you nonsensical answers, but it's not because you did something wrong, it's because Mathematica assumed something you didn't assume. And sometimes you have to massage the expression a little bit in order to get what you need. Alright, that's it for today. In the next lecture, we're going to consider shift theorems which connect the shifts of the function with exponential multipliers for Laplace transforms and exponential multipliers for functions into shifts of Laplace transforms. Thank you for listening, and I'll see you in the next video.